Welcome to The Explainer. Every time you click something or type or even just see a pixel on your screen, it's all thanks to this lightning-fast, totally invisible system of storage and retrieval. Today, we're going to pull back the curtain and really dive into what's happening inside your computer's memory.
Okay, so here's what we're going to cover. We're going to start right at the very heart of the computer, inside the processor, and work our way out, layer by layer. We'll look at the CPU's inner circle, its main workbench, and even its giant digital warehouse. And it's all in the name of understanding how this whole complicated system solves one huge fundamental problem, the need for speed.
So yeah, this entire super complex memory system that we're about to unpack, it really only exists to solve one single massive problem, a huge speed gap between your computer's brain and, well, its working space.
So why is this even a problem? Well, imagine you've got a world-class sprinter paired up with a marathon runner for a really short relay race. The sprinter, that's our processor, is just unbelievably fast, but they're constantly having to slow down, turn around, and wait for the marathon runner to hand them the baton. That handoff, that waiting time, that's everything. And it's exactly the problem this whole memory hierarchy is built to solve.
And here's the core of that issue, laid out right here. Your CPU, your processor, it's literally thinking in nanoseconds. That's blazing fast. But the main memory, your RAM, it just can't keep up. And that speed gap creates a bottleneck, forcing that lightning-fast CPU to just sit there, waiting for data. And that little bit of waiting, it affects everything you do on your computer. So how do you fix this? Well, to bridge that speed gap, engineers got clever. They created a layered system, a hierarchy. And we're going to start with the memory that's literally built right into the CPU itself. This is what we call the CPU's inner circle. The very first layer is called register memory. You can think of registers as the immediate thoughts in the CPU's mind. So if the processor is calculating, say, 2 plus 2, the numbers 2 and the instruction to add are held right there in the registers. It is the absolute hands-down fastest memory possible. But, and this is a big but, the trade-off is that there's very, very little space. Okay, so if registers are the CPU's immediate thoughts, what's next? That would be cache memory. And the best way to think about cache is like the CPU's personal notepad, or the stuff it keeps right on its desk. It's a small, super fast buffer that holds on to information it uses a lot, so the CPU doesn't have to make that long, slow trip all the way out to the main memory every single time it needs something. But it gets even more interesting, because cache itself is split into different levels, and this is where you really see the core trade-off of the whole system in action. You've got L1 cache, which is the tiniest and the fastest. It's often even split into one part for instructions and another for data. Then you have L2, which is a little bigger and a tad slower. And finally, there's L3. It's a much larger, shared pool of data that's still just incredibly fast compared to the alternative of fetching something all the way from RAM. All right, let's take another step out and see how this all builds up. We're moving to the next layer, the main memory. This is your computer's active workbench, and you probably know it best as RAM.
Now, a really crucial distinction we have to make here in primary memory is between volatile and non-volatile. Volatile memory, like your RAM, needs constant power to hold on to data. Think of it as a temporary workspace for all your open apps. The moment you power down, poof, it's wiped clean. Non-volatile memory, on the other hand, holds on to its data no matter what. Power on, power off, it doesn't care.
And, even RAM isn't just one thing. It comes in different types for different jobs. This table really breaks it down. You've got static RAM or SRAM, which is crazy fast, but also really expensive and power hungry. That makes it perfect for that CPU cache we just talked about. Then you have dynamic RAM or DRAM. It's simpler, it's cheaper, and that's exactly why it's used for your computer's main workbench. The gigabytes of RAM you see listed on a spec sheet.
And that DRAM in your computer, it hasn't just been sitting still for the last few decades. It's evolved a ton. We've moved to these amazing technologies like double data rate, or DDR. What this basically does is use a clever trick to double the processing rate by fetching data twice for every tick of the system clock. And what does that mean for you? Well, simply put, a faster, much more efficient system.
So, the other side of this primary memory coin is ROM, which stands for read-only memory. Now, unlike RAM, which is all about active work, ROM holds the permanent, unchangeable instruction manual that your computer reads every single time it boots up. This is what we call the BIOS or the firmware.
And just like RAM, ROM has evolved too. It started out as truly unchangeable, programmed once at the factory, and that was it. But over time, it got more and more flexible, leading to what we use today, EEPROM.
This stuff can actually be updated with new firmware electronically. So yeah, no UV light required anymore.
Okay, now we're going to take the biggest step back from the CPU so far. We're moving from that active workbench out to the vast permanent digital warehouse. This is where all your files, your applications, and your entire operating system live for the long term.
This is your hard drive, or your SSD. It's the warehouse. It holds huge amounts of data, and it holds it permanently. But, and this is key, it's much, much slower to access. So for the computer to work on any file, it has to first go all the way out to this warehouse, grab the file, and bring it back over to the workbench, which, as we know, is the RAM.
In this warehouse, it comes in a bunch of different forms, right? It could be the spinning magnetic platters of a classic hard disk drive, or the flash memory chips inside a modern solid-state drive. It can even be remote servers that you access over the internet, something we all just call cloud storage.
Okay, but what happens when your workbench, your RAM, gets totally full with open programs? I mean, we've all been there. Well, your computer has one last really clever trick up its sleeve to create the illusion that it has almost infinite memory.
But first, let's understand the problem this trick was designed to solve. It's called fragmentation. In older systems, memory was like a parking lot with fixed reserved spaces. So as you can see here, after program A closes, we have plenty of total empty space, but it's all broken up. So a new, bigger program can't load because it can't find one single continuous spot that's large enough to park in. It's a real headache.
This is where virtual memory comes in and saves the day. Your operating system does something brilliant. It uses a part of your slower, but much more spacious, secondary storage as an overflow area. So when your RAM gets full, it takes the data from a program you're not using right now and temporarily moves it to a swap file on your SSD or hard drive. This frees up precious RAM for whatever you are working on, and it creates this amazing illusion of a much, much larger workbench.
So there you have it. We've toured the entire hierarchy, from the CPU's immediate thoughts all the way out to the big digital warehouse. But what does this all actually mean when you're looking at the specs of a new phone or a laptop or a gaming PC?
Here it is, the whole system in one neat pyramid. And it really is all about trade-offs. At the very top, you've got those tiny, unbelievably fast registers. And as you move down the pyramid, the memory gets way larger and a lot cheaper, but it also gets slower and physically farther away from the processor. All the way down to your huge but, let's be honest, pretty sluggish secondary storage.
So here's the crucial takeaway. These specs, they're not just numbers on a box. They directly impact how your device actually feels to use. That cache we talked about, more of it means your computer doesn't have to reach out to slower memory as often, which makes everything feel snappier, especially when you're multitasking. More RAM? That's what lets you keep, 50 browser tabs open without your computer grinding to a halt. And believe me, upgrading from an old spinning hard drive to a modern SSD for your secondary storage, it is the single biggest upgrade you can make for a system to feel fast and responsive.
This whole elegant pyramid of memory is constantly evolving, always trying to keep up with our crazy demands. From the very first computers to today's AI-powered devices, the story of computing is really the story of bridging these speed gaps, which kind of leaves us to wonder, what brilliant new solution are engineers going to invent to bridge the next one?